Welcome back. In this lecture, we are going to solve another dynamic programming problem called Levenshtein distance. In this problem, we will be given two strings and we have to calculate the added distance between them. That is, we need to find the number of minimum operations required to transform one string into other. There are three operations that we can perform. We can insert a character, we can remove or delete a character, and we can substitute or replace the character. For example, we have two strings, base and basic. We can convert base to basic by substituting E with I and then inserting character C. Though there might be other ways, but the minimum added distance will be 2 here. And if strings are Thursday and Tuesday, it will take two operations as we need to delete letter H and replace the letter R with E. If we think of subproblems, we need to process all the characters of these strings. Suppose we traverse from the right side and we compare the last characters. If they are same, we don't need to do anything. We ignore them and check for the remaining characters. And if they are not equal, we have three choices. Either to insert the character of string 2, or to remove character, or replace the character with the character that we are comparing. So the subproblems here are, if the length of first string is m and the second string is n, then in the case when the characters are same, we ignore them and we check further for length m-1 and n-1. In other case, if we insert character, length for string 1 gets m+1 and string 2 gets n-1. So if we go with this choice, we need to further check for remaining lengths, which will be m and n-1. Similarly, if we remove last character, we will check for length m-1 and n. And if we substitute character, we further check for length m-1 and n-1. So we calculate number of operations in all three choices. Whichever is minimum, we go with the choice and add 1 for the current operation to it. We keep on doing this till we end up traversing one of these strings. In that case, the number of operations will be the length of the other string, as the only option will be to insert the remaining characters. So if the length of string 1 gets 0, then the minimum added operations will be the length of other string, which is n. Or if the length of other string, the string 2, gets 0, then the minimum added operations will be the length of string 1, which is m. Let's see the recurrence relation. Levenshtein distance for strings having length m and n will either be the distance for m-1 and n-1 lengths, that is the case when last characters are equal, or 1 plus the minimum among the distances that we calculate for all the possible choices, that are when we insert the character, when we delete the character, or when we replace the character. Or it would be the max of m and n, that is the base case, where one of the string is of length 0. Now to optimize it a bit, we can merge these duplicate recursive calls. So what we do, we put k here, where k will be 1 when we replace character and 0 when last characters are same. If we draw recursion tree for this, for each recursive call, we need to make 3 recursive calls with lengths m n-1, m-1 n, and m-1 n-1 respectively. So clearly we can see there will be many recursive calls with similar arguments. That is, with this approach we are solving similar subproblems again and again. So to avoid solving the overlapping subproblems, we can go with dynamic programming where we solve smaller subproblems and use those solutions to build the final one. So first approach is memorization or top-down approach. So we will store results of subproblems in an array. As here are two varying arguments, we build a 2D array of size m and n, and that is initially filled with -1. Then we solve the problem and store the result of each subproblem at the position m-1 and n-1, so that whenever this function is called to solve for the similar subproblem, we just return the result. So at every call, we put a check if the problem is already solved or result is already present. So if it is present, we take that result instead of calculating it. Let's see the final approach, which is bottom-up to solve Levenshtein distance problem. As we did in previous approach, we create a 2D array to store result of all the subproblems, but this time we create array of size m+1 and n+1. Why? To handle the base case. That is, for 0th row and 0th column, we initially update the length of other string. As to convert a blank string to BAS, what we need to do, we will need to perform 3 added operations. So we update 0, 1, 2, 3, 4, 5 at 0th row and 0, 1, 2, 3, 4 at 0th column. Basically, at each index of this array, we will store the minimum number of added operations that we can perform on a substring of string 1 to turn it into another substring of string 2. How are we going to do that? Let's understand. We start from 1 and 1. So letters are B and B. These are equal. We need not to perform anything here. So we check for remaining string as the number of added operation will be the one for the remaining string. So we can see here there's nothing. B is the first character in both the strings, so we update the added distance for 0, 0, which is 0. Now for 1, 2, B is not equal to A. So what can we do here? We look back here, B and B are same. So we just need to insert A. Or we delete B and insert B and A. So minimum of these all possible operations is inserting the character A, so it becomes 1. So we update 1 here. Next is letter S. B is not equal to S, so we look back to convert B to BA. It took one operation, so here we can add 1 to this and update 2. Similarly, for I, it will be 3 and for C, it will be 4. That means to convert B to BASI, it takes 3 operations and to basic, it takes 4 operations. Now next is letter A and B, or we say we need to convert BA to B. In that case, we have choices. We remove A, we remove B, that are the 2 operations, and we add B, so it becomes 3. Or we substitute B with A, that is the 1 operation, and then we remove A, so it becomes 2. Or we just say B is already there, we don't need to do anything, so we just remove A, so that will happen in just 1 operation. So here 1 is the minimum, so we update 1 here. So what is the pattern here? At every index, we are looking for these 3 neighboring indices, and we are choosing the one which is minimum and then adding 1 to get task performed. And that's the case when characters are not equal. If they are equal, we go diagonally and update the added distance for the remaining strings. So the formula is we compare the I minus 1th and j minus 1th character, as we are starting from 1 1 to fill up this array here. So for iteration I and j, we're gonna check if I minus 1th and j minus 1th character are equal. We fill up the added distance for I minus 1 and j minus 1 position. If not, we look up at the three neighboring indices that are at I j minus 1, I minus 1 and j minus 1, and I minus 1 and j. So we pick up the minimum one and add 1 to it.